Hello and welcome back to this mini-series on quadratic equations. So this is episode 3 of what's likely to be 5, and in today's video we are going to be looking at examples of quadratic equation in use. So we're going to have two examples today. The first one which will come up at a GCSE level, and the second one which will come up at an AS level. But it will show why quadratic equations are useful and important. So let's set up a scenario where you have somebody standing on the ground and he has a ball in his hand, and they throw the ball from 1 metre off the ground into the air with an initial speed of 10 metres per second. The ball's going to go up in the air and then come back down. Now let's say we wanted to find out what time the ball was 5 metres above its starting point, i.e. 6 metres above the ground. What we need to do is use something called the Quadratic equations, because the ball is going to decelerate linearly as it goes up, and when it reaches its highest point its speed is going to be 0, and then it's going to accelerate back down to Earth. So the Quadratic equations are a series of equations that you learn at GCSE, which tell you about the motion of the ball, and it divides itself up into S, which is displacement, U, which is the initial speed, T, which is the time, A, which is the acceleration, and there's also another symbol they use, which is V, which is the final velocity, which we won't be using today. But this equation, as you can see, has a t squared term and a t term in it, so it looks like a quadratic. So we can use quadratic equations to solve this. So we want to find the time when the ball is 5 metres above its original starting point. So the displacement is going to be 5. That's going to be equal to u, which we said is 10 metres per second. And the important thing about solving these is to keep your orientation the same throughout. So I'm going to be assuming that going up is positive and down is negative. So we initially got the speed going up, therefore we've got positive 10t. We've now got this half at squared. So the half stays as a half. The acceleration due to gravity I'm going to take as 10 metres per second. I know it should be 9.8, but for this example I'm just going to use 10 because it makes the maths a little bit easier. And because acceleration is acting downwards, i.e. we're accelerating when we go up, accelerating when we go down, it's going to become minus. So I'm going to put minus a half at squared. And the a is going to turn to 10. So I can now tidy this up and bring everything to the same size. So I'm going to leave the 5 where it is. I'm going to bring this half times 10t squared over to the other side. And because we've got a half times 10, I'm going to change that to 5. So we're going to have 5t squared. This 10t is going to come over and become minus 10t plus 5 is equal to 0. So I've now got my quadratic form that we've talked about in previous videos. As you can see, there's a common factor of 5, so I'm going to take that, divide through by 5. So dividing through by 5 will give t squared minus 2t plus 1 equals 0. So in the previous video, episode 2, we looked at 3 different ways of solving quadratic equations. I'm not going to use trial and error. I'm looking at this and seeing, is there a number which when multiplied together makes 1 and when added together makes 2? And I can think of a number that does that, it's 1. So I'm going to try using the factorisation method because it's going to be quicker in this case. So I'm going to open my brackets, set them equal to 0. I'm going to put a t at the front of each bracket. So my first sign goes in the second bracket. My second sign is a plus, therefore it says the 2 bracket signs must be the same, so this is also going to be a minus. And then I'm looking for those 2 numbers which when multiplied together make 1 and when added make 2, and that's going to be 1 and 1. So this would give the form that one of these brackets has to be equal to 0. Therefore, t minus 1 equals 0, or t minus 1 equals 0. Of course, those are both the same thing. So in this case, t is equal to 1 second. So the time when the ball is 5 metres above its original starting point is at 1 second after the ball was thrown. Because we've only got one real solution for this, or say one solution, which is a second, this actually tells you that when the ball is at 5 metres above its original starting point, or 6 metres above the ground, is when the ball is effectively travelling at 0 velocity, is the turning point. So 5 metres also happens to be the max height that this ball will reach. If we picked a distance that was higher than that, or displacement that was higher, what you'd find is that there would be no real solutions for this equation. So it tells you that the ball would never reach 6 metres. If you picked any height between 0 and 5, we would end up with two solutions. So one where the ball, or two real solutions, or valid solutions, one when the ball was on its way up and one when the ball was on the way down. If we put in a displacement of, say, minus 1, so we're looking for when the ball was below the original starting point, what we'd find is that one of these brackets would be positive, one would be negative. Therefore we'd have a positive time, which is the ball hitting the ground, and a negative time, which isn't real. It's not a real solution. Therefore we exclude that one. So you can try those yourself, and next up is an example of finding the volume of a box. So this is the second and final example for this video. So let's assume you had a sheet of paper that was 20 centimetres by 15 centimetres. If you cut little squares out of the corners, you can fold the edges up along these dotted lines and you could make a box out of them. And let's say you wanted to maximise the volume of your box. What size square would you have to cut? So I'm going to say that the size of the square, or the side of the square, is going to be x centimetres. So first of all, we can have to write out an equation that allows us to find the volume of this box that we make. So volume is length times width times height for a rectangular box. So we can start off by saying, well, the length is going to be that 20 minus, and then we're going to have a box cut at either end, so we're going to have to take 2x off it. So that's going to be equal to the length. I'm going to multiply that by the width, which is going to be 15 minus 2x. And then that's all going to be multiplied by the height of the box, which will be x. So this is going to be equal to the volume. So I'm now just going to multiply this out. So we're going to have 20 times 15, which is 300. Then I'm going to leave the x to the end. So then we've got minus 2x times minus 2x, which is minus 4x squared. We've got minus 2x times 15, which is minus 30x. And we've got minus 2x times 20, which is minus 40x. And this is all going to be multiplied by x, which is going to be equal to the volume. So I'm going to bring my terms together and multiply out. Sorry, there should be plus here. So we've got 4x squared times by x will go to 4x cubed. We've got minus 30x minus 40x, so that's going to be minus 70x, times the x goes to x squared, plus the 300 times x. So this is the equation for the volume. So as you notice, this is not a quadratic. because we've got this x cubed term. It's actually a polynomial equation. So how do we now find a value for x that maximises the volume of the box? So we're going to use a technique called differentiation. And what this does is find a gradient of a curve, and it comes up at the AS level. That's where it gets introduced in the British education system. So if you plotted this out a graph, it would look like a waveform, or it'd have a couple of it'd have a peak and a trough on it. The peak, so this is a volume versus x graph. So the peak is going to be where the maximum volume is, and at the peak the gradient becomes 0. So if I can find the gradient of that, find the point where the gradient is equal to 0, then I can work out what value of x that is, and that's going to be the amount I need to cut off to make my squares. So the differentiation of this, we're going to go 12x squared minus 140x, so plus 300 is equal to dv by dx. I'll make a video about differentiation, or a separate video about differentiation, where this all gets explained, but this is how this is differentiated. And as I say, when this is at a maximum or a minimum, the gradient is going to be equal to 0. So we've now got effectively something that looks like a quadratic equation. This is divisible by 2, so I could go 6x squared minus 70 plus 150 equals to 0. But what I'm going to do is just go straight into using the quadratic formula. So the quadratic formula is minus b plus or minus the square root of b squared minus 4ac all over 2a. So this is equal to minus b, so that's 140, plus or minus the square root of minus 140, or sorry, the squared. So I'm just going to put that right down as 140 squared. I could put the minus in. Minus 4a, which is 12, and c, which is 300, all over 2 times 12. So this is equal to 140 all over 24 plus. I just had to reset the battery on this. So working out this square root here will give a value of 72.11. So when I plug this into a calculator, we're going to have 140 plus 72.1 all divided by 24, which will give 8.84 centimetres. Or when I do the minus 1, what I'm going to end up with is 140 minus 72.11 all over 24, which is 2.83 centimetres. So these are the two values that you could cut your squares to be in order to maximise the volume. However, with this 8.84, if we double that, which we need to do to be able to remove it from both sides, it's going to be equal to 17.68, which is more than the width of the original piece of paper. So we can't remove that from the paper. So in that case, this is the only real value. So if you want to maximise the volume of your box, you need to make your x equal to 2.83 centimetres. So in the next video, I will look at factorising in more detail, and in the final video, I will look at another method of solving quadratic equations.